Welcome. I'm Christoph Rohringer from INTEC, which is a non-university research organization in Austria. And I'm very glad today that after almost 3 years of the IEA task 43 on unlocking the hidden potential of thermally activated building mass energy storage, we can present you, let's say, an array of preliminary results. I'm joined today by several speakers from the task, which I want to thank also for their time and also their contributions to the task. It's also a joint organization with a national project of ours, which is called BT-TAP. It was a monitoring study on TAP buildings that are present in the Austrian ecosystem. My role today is in the next 10 minutes to lay, let's say, a little bit the foundation so that you know the different talks that are going to be presented today, where they are situated in the task and what actually our goal was. So let's start with the motivation. Thermal building mass storage, aka, let's say, pipes in concrete, is not something very new. So this is probably not the reason why you participants dialed in here today. This is a known technology. And if you check the Wikipedia definition of thermal building mass activation, you find this text. Yeah, it's a technology to regulate temperature, and they are used for cooling of a building, usually office buildings, but increasingly so residential buildings, and for heating. However, if we think a little bit further and envision a world where we maybe overheat or subcool these components to feed off of the stored energy at a later time, it could also be an energy storage. And this is a thought that occurred to us 3.5 years ago, actually, and we thought, okay, this is an interesting perspective on taps that it's not widely used. Let's try to find international experts who see it the same way. And I think this has succeeded. We had quite a good exchange the past 3 years. And now we really say, okay, we could use thermally activated building mass as a storage for volatile renewables in structures that are already there, that are already built. What was our goal then with the task? So I can speak very clearly, I think, for Austria, but we found it in different countries as well. TAPS is there, but it's usually implemented by experts. And we figured it would be nice if we could prepare the thermal activated building mass energy storage for a widespread, kind of standardized and economically attractive integration, which is just not there yet, but beginning to be so. And in order to reach this, let's say, ultimate goal, we found 4 main areas where we wanted to work on. So the first one was, how can we build such storages in new construction and also in refurbishment? Also, how can we operate them and integrate them into systems? So one building alone is probably not so interesting from its flexibility point of perspective, but 100 maybe, 1,000 definitely, 10,000. Then also we asked ourselves the question, how can we do business with such a storage? And how can we satisfy the end customers and the residents? Because here we have a very special kind of energy storage. This is an energy storage where people are living and working in. So there's an additional set of constraints we need to be wary about. And lastly, we wanted to increase the reliability and the trust in the technology. So how can we convince investors that what they are buying has a clear benefit and also, an expected benefit? So how can they know what they are getting? These 4 questions basically translated into the subtasks of our task. For people who are not so familiar with the IEA, these kind of work packages is probably the closest word. Each subtask has a subtask leader, and I think many of them are present today. So we have one subtask dealing with construction techniques and materials you can use. Is it concrete? Is it wood? Or maybe brick? We have a subtask on system integration and control. So these TAPS energy systems, they tend to have very high time constants, so they react very slowly. So you need to control them properly. We have the subtask C on, we summarized it as non-technical challenges. So how to do business, how to ensure indoor climate comfort. And these are more scientifically oriented. So we looked at different research projects, and then we figured for the market interaction or for the transition to market, we need an additional subtask, which is the subtask D, who deals with standardization and KPIs. So how can we take all these scientific facts and translate them into something that's useful for the market? Since we're very much interacting with the building, we were also in touch with 2 of the EVC annexes, so a different branch of the IEA, the Annex 82 and the Annex 84, and this was also very fruitful, I think, for all the 3 activities. So brief look into the subtasks. The first one is subtask A, construction materials, which is led by John Grunewald from TU Dresden. He's also in the meeting today, so if you have any questions to him, you can use this time today during the discussion at the end. basically, the subtask looked at different materials and material combinations. You can see here, for example, a prefabricated wood panel instead of the usual concrete. We looked at construction manufacturing strategies in new buildings. This is the middle picture, and I'm very happy that the CEO of Innogration GmbH, Thomas Friedrich, is also here today and giving a talk about their sandwich panels. I think very interesting, prefabricated panels. But the same is also true for refurbishment. So we have a lot of building mass that's not yet activated, but it's already there. And here we have the head of R&D of SEPA Solutions, which is an Austrian manufacturer who has a solution developed to activate existing building mass. And of course, we wanted to look at zoning. So how do you do the circuits so you are flexible in control and repurposing of the building? As I said already, TAPS is a slow-moving technology, let's say, because there's such a high thermal mass and inertia. So you need to properly control it. And this is what subtask B was all about. It was led by best research by Daniel Muschig from Austria. He's a control specialist. And they did many projects how to model the thermal zones in such buildings and also use smart control. And on the bottom right side, you can see, maybe we can do the laser pointer. You can see how very poor control is affecting the indoor climate comfort. So usually the comfort should stay within this band. It's very much out of there. But then they adapted the control. They did nothing to the hardware. It's just the control. And all of a sudden, it's a very well-controlled building and technology. So really crucial aspect of thermally activated building mass. Subtask C had, I think, the very big task of summarizing all the non-technical challenges. I think one of the major outcomes is that David Ritter is a main author, together with many co-authors, one of them being Professor Shady Attia, who's also in the meeting today, wrote a paper on the non-technical challenges of how to accessing the TAPS as an energy storage. So you can see here a graph there with all the stakeholders that are involved in this process. And it's already available as a preprint. But also this subtask looked at the indoor climate comfort. And actually the subtask lead, so Aalborg University from Denmark, Alelisa Afshari, he's an expert in indoor climate comfort. And also here today, I hope for your questions. And then lastly, standardization and KPIs was led by Technische Universität Darmstadt from Germany, by Joscha Reber, also in the meeting. And this was basically the transition from all the scientific knowledge into something that is practical in industry. We looked at different sets of KPIs to describe the TAPS, to to judge their performance and to predict their performance. And we also looked at a lot of different buildings that we found with TAPS. And I think that the biggest source of those was the Austrian monitoring project BT-TAP, which is represented also by a talk by my colleague Walter Becke today in this OnSeminar. So you can see quite a broad scope to really look into every aspect that is needed to make the thermally activated building mass work as an energy storage. And this is also how we selected the talks today. So here for your overview is the speakers and their topics. So we will look at the monitored buildings and the KPIs, the construction techniques for new construction and also with prefabricated panels, the construction techniques used in refurbishment, and the, let's say, the EU rules, barriers, and policy pathways that are needed to actually allow TAPS to be operated as an energy storage. This is my last slide. Just an overview where task 43 is standing at the moment. So we will conclude the task at the end of 2025. So we are at the cusp of finishing it. There's just one task meeting left and already a substantial part of the final report written. We are expecting that the international report will be finished by summer. So our draft will be ready in February, and then there's a loop with the EXCO to ensure the quality. And we hope that in summer we have the publishable report. And as Stephanie already mentioned, today, after all the presentations are done, so basically we're providing a lot of input, there is the opportunity to discuss with the panel, so with the speakers, but also there is several subtask leaders of task 43 already in the meeting. And yeah, I would be glad if you use this opportunity to engage with us, try to find out more about thermally activated building mass. And with that, I thank you for your attention.
Okay, thank you very much, Christoph, for the quick overview. And I directly hand the mic over to Mr. Walter Becke, who will give some insights to the BT-TAP, as we just heard.
Yes, thank you for the introduction. Let's see. Now that should work, I think.
Yes.
So welcome to my talk about our national project. This project was actually a direct order by the ministry within a certain funding program called City of the Future. And we gathered a project team that, consisted of science partners on one side, which is ourselves as project coordinators, E7 and Hakon. These were the partners on the technical side. And we also had on the social science side a partner who did the surveys and interviews around all the demonstrators. And we also had two engineering offices in the project team. On one side, Future is Now, which is one of the pioneers of TAPS within Austria, and Hakon. This is kind of a double hat for them. They are on the science side as well as on the engineering office side. And we also had the University of Applied Science of Salzburg, which brought in some industrial knowledge on one side, and also there's an accompanying research for another funding program that's focusing on TAPS in Austria. Yeah, you already saw this slide from Christoph before. So these were all our demonstrators. And we made sure by selecting those demonstrators that we had a variety of applications available. So you can see on the left side quite a few residential buildings. You can see on the top a few educational buildings, and all the others are basically office building plus something. So there are laboratories in between. There are the production halls, and so on and so on. The main goal of the project was to find out what tabs are used for and how it works in the field. We did comparison based on measurement data, surveys, and interviews. So we asked actually the users inside the buildings how they feel about sitting in a thermally activated building or living there. And we also talked to those who planned the building and who run the buildings now, and those who decided to actually build one such a building. And well, what we still have to do is to do a summary of all the results and well, make it available to future decision makers to decide if they want to use, hopefully decide to use those tabs. Now I give you a short overview about where those demonstrators are located. So basically they're all over Austria, which was also a requirement by the ministry to find actually buildings all over Austria. And like also every usage should be distributed over all of Austria. And there was a second requirement. I think that's quite important. All those buildings should be built or should have been built without a science input. So actually all those buildings are built out of the field. And yeah, that's kind of the state of tabs in Austria represented. We also made sure that we have different activated materials available. So it's not a big surprise that most of the buildings or most of the components were concrete. So in 18 cases, it's concrete. In 2 cases, it's actually solid wood that is activated. And one of the buildings also had an existing wall activated. So actually a refurbishment. We also tried to have different components activated. So in most cases, it's the ceilings. And if the ceiling is activated, it's usually for heating and cooling. Then we have in 6 cases the floor activated, which is usually or mostly for just heating. And in one case, we have the wall, which is the refurbishment mentioned before, which is also just heating. And then you see here the actually heating and cooling energy consumption of those buildings. That's in kilowatt hours per square meter area and year. And you can see actually it's quite a range. So on the left side is the heating, and on the right side is the cooling. So we have everything between a passive house and well, more energy demanding building, but in the median, it's usually rather good buildings. So it's 40 kilowatt hours per square meter and year for heating, and for cooling in the median, it's around 12 to 13 kilowatt hours per square meter and year. So this is the actual consumption measured. And what's quite interesting is that the cooling demand in the forecast is pretty close to what we measured in the field, while on the heating side, the actual heating consumption in the field is usually higher than the forecast. And this is closely connected to the actual room temperatures we saw, but I will show you that in one of the upcoming slides. So this is a very, let's say, condensed results of the measurement. You see typical spreads between flow and return temperatures at full load for heating and cooling on the left side of the slide, and also divided between those different activated components. So for heating, for instance, if heating is done over the ceiling, then the typical spreads between flow and return temperature is about 4.5 Kelvin. And for the floors, it's a bit higher. And for the wall, it's even higher. The reason behind this is that for the walls, for instance, you have the existing wall and you have to apply tubes from the outside. And then you have to make sure that the heat coming in the tubes passes through the existing wall into the room. So you usually need higher temperatures to achieve that, which you can see on the right side. So you see at full heating load, in that case, 50 degrees centigrade were needed to make the room inside comfortable. For the floors, you see a higher temperature difference than for the ceilings. The reason behind that is that the floor activation was mostly used in warehouses and production halls. So they are usually less insulated than office buildings or residential buildings or rooms. And that's resulting in a higher temperature difference for heating. And on the cooling side, you have a smaller temperature difference. That's usually because the comfort requirements or the temperature requirements for halls, production halls, warehouses are lower than for office or living rooms. And if you look on the very right side, you see the typical flow temperatures for heating and cooling. So in all cases, it was free cooling or passive cooling. So you just use a borehole or a ground collector to run the temperatures that coming out there through the tubes. And yeah, we have in all cases quite moderate temperatures. So on the heating side and on the cooling side. And yeah, there's this connection between the temperature differences and the moderate temperatures. Now, the big advantage for those moderate temperatures is that this allows an efficient use of heat pumps and free cooling or solar thermal. So basically renewable heat and cold. Now let's have a look at the room temperatures. What you see here is hourly mean values over a whole year for a residence building. The colors in the background basically mark the comfort zones according to Austrian standards. So green is very good and yellow is a little bit worse, and red is even more worse. And this is like normal year, what you would expect. So January is on the left and December is on the right. And what we see here is that the temperature over the whole year is very balanced. Okay, it does according to how the sun goes or the day goes. There are slight variations, but those variations are within a small band between 23 and 25 degrees. So this is very comfortable, stable room conditions. But the conditions are quite higher than what's usually used in the forecast. So in Austria, usually the forecast is done for 20 to 22 degree room temperature. As we have quite higher temperatures, this results in a higher heating demand. What we also did is we did quite detailed comfort measurements with a measurement tool that you can see on the top right. So this measures temperature at different height levels in the room. It measures the air velocity in the room, the black globe temperature, and the air humidity. And the curves you see here are just temperatures. And what we see here is that all temperatures, in various heights of the room and the black globe temperature are very close to each other. So it's very, very close because the axis on the left side, you see the differences are between 21 and 23.5 degrees. So it's basically nothing. And it's pretty much the same in summer and winter. So even if you look very detailed into the comfort, you will see that those thermally activated buildings have a very, very high comfort level. What's also quite interesting in this slide is that in winter, you see 2 days with a lower peak. And those 2 days are actually a weekend. So during the weekend, there is less or no heating being done. So what you actually see here is the capacity or the storage capacity of those taps. And if you look at it, you can say over those 2 days, this building lost about half a Kelvin of temperature. So this is actually, that's the storage potential of what Christoph mentioned in his introduction. And speaking of this storage potential, there's actually quite a wide range of possible usage. And I'd like to show this on 2 examples. Like we have 2 extremes. We have on the one side kind of a passive usage of those storage capacity. On the left side, you see a building. It's actually quite a huge building with a office part and a huge part of a storage hall. And the total heating load of this building is 1 megawatt. And the whole building is supplied with a heat pump with a maximal output capacity of 270 kilowatt. So it's quite below the heating load. And this only works because the taps actually reduce the building peak load. And of course, the heat pump runs 24/7 at maximum power, which is usually the optimal point of operation. And this works because of taps. This is like the passive use. And in our demonstrators, of those 16 we had, 4 applied this usage of storage capacity. And then we have the active usage. And there I have this example of this building. This is an educational building that's sitting in the middle of nowhere. There's really nothing around, and it's entirely cut off any grid. So there is no electricity grid there, and there is no thermal grid there. You see on the roof are some PV panels, and on the hill on the left side are some solar thermal collectors. And these and there's also a earth collector in the ground, which will do the cooling in summer. So, and this building works because of the active usage of the storage capacity. So there's quite some concrete there. The ground slab is 50 centimeters thick, and the ceiling is solid wood, I think, of 30 centimeters. And this storage is used when the sun is there. In winter, the solar thermal just fills up what's possible into those slabs. And over the night and over the time where there's no sun, there's this storage capacity that's actually heating the building. So this was applied in just one case, and all the other demonstrators we've seen are in the middle between them, or actually not using the storage capacity and running the taps basically as a floor heating. So one of the main findings was that this utilization of the storage potential should be increased, can be increased, and should be increased. And I'd like to finish my talk with a placative visualization of what this storage potential is or could look like. I brought you a visualization of one of our demonstrators, which is a resident quarter in Vienna that's actually using taps. And if we calculate the storage capacity of those concrete slabs in that case, using a temperature difference of 4 Kelvin, and transform this into a tank storage with a temperature difference of around 70 Kelvin, then we get a tank storage of a certain size, and we have to put it somewhere. And we can, for instance, just put it in the street. So, and this results in quite a few disadvantages that are listed on the left side. So basically, you need a lot of room to put the storage somewhere. You have quite a few heat losses, especially in summer, that go to the surroundings where you cannot use them. You still need some hydraulic connections to all the buildings, and you need heaters or heat and cold distribution system in addition to the tank in the building. You have to have the maintenance for everything, and also it costs extra because you have to build the tank. So my conclusion for this is we have existing building mass that can be activated, and therefore we should activate it and use it as a thermal storage. Yeah, so that's everything from my side, basically. So as a conclusion for everything, we found that active usage of the storage capacity is not applied yet. It's because of two reasons, basically. There's the technical side, so people have to know how to control this, and that's not so easy for everyone in the field yet. And there are some regulatory hurdles as well. There's an extra talk after me. We see that, or we saw that a wide range of materials can be activated and we can apply taps to different kinds of building, so buildings of various uses. And we see in all buildings a very high room comfort. And the moderate operating temperatures are just great for using renewable energy. So yeah, let's transform our building that are already there to be actually heat and cooling dissipation surfaces. Yeah, thank you for your attention.
Thank you very much, Walter. It was a very nice summary of all these interesting results. The next speaker is Thomas Friedrich. So as it was a little bit spoiled already, it will be about a new construction. I'm curious about your talk.
Yes, thank you very much for the introduction. I am from the I am an engineer who produce these elements, and then these elements are being we sell these, and we support the people using this technology, and we use a special technology. You see, as the word means, thermal activated building. It is what we think we will use our buildings, the structure of our buildings, to manage all as well the thermal storage. As you can see here, the idea of our concept is that we use slab system with a sandwich cross section. As you can see here, then you have a lower part of the slab, the ribs of the slab, and then it will be joined with an upper part of the slab. And in the slab itself, you have all the registers for the pipes, which will be connected all together. Additionally, you can use also air elements to bring the air into the room. And I just show you two slides from buildings we just recently finished. You see modern buildings look like this as a glass facade, and the inside of the building something looks like this. You have a very large area with glass, and then there comes heat and cool inside here. But we managed to realize the comfort zone in this room only by the tap system, as you can see here on the upper part. Additionally, we use also acoustic elements, as normally concrete ceiling is very hard in acoustic, so we have to do something to work against these hard elements. Another building, as you can see here, is also one with a total area of glass around the facade, and the inner part looks like this, also a concrete ceiling where we have the tubes inside, and here you can see again the acoustic elements which are incorporated into the concrete slab. I just give you a short overview. The idea of the thermal activated building started about 1920, and then that was used in flat slabs. As you can see here, you have a cross section, a full cross section, and in the middle of the cross section you put in these registers. And the alternative I just want to mention is what you can see here. We have these split elements on the facade, and we do not want to have our facades looking like this. Therefore, we need the thermal activated elements in our slab system. But we need to clearly distinguish between a cross section of full concrete, cross section full concrete where we put the tubes on at the surface, and exactly what we do. We have a sandwich cross section with an upper shell and a lower shell, and in the lower shell we put in the tubes, and that makes a certain difference to the behavior of these elements, and that is what I want to show you. You see here the traditional one with a very big cross section, full cross section. You put in the tubes in the middle, and then you heat it, and you can see here the heat goes up here and goes up in the upper part, but it is needed at the lower part. I think we have the thermal storage, but we also need to have the comfort to bring the energy into the room. And you see here, it is not fully possible to bring the energy. It takes time to bring the energy from the cross section to the surface of the ceiling. So that is what we are doing. We have this kind of cross section, which is a sandwich cross section with the upper part shell and the lower part of the shell. And in the lower part, we have these tubes for heating and cooling. And these holes are made for the acoustic elements, which are incorporated in a later phase. So, and additionally, you can use this area, this cavity, for bringing all the pipes and tubes together. One big advantage of the sandwich cross section is that you save a lot of concrete, and additionally you save a lot of warming potential. And you can see here a cross section with a span like this. You have a global warming potential with a flat slab like this here. This is this line, and when we use a cross section, you have this line here, which is more or less stable because we only enlarge the ribs and not the main part of the two the two shells. And this is the savings on global potential. And you can see here, if you use a cross section, you can save a lot of global warming potential by these sandwich construction compared with the full construction cross section. And coming back to our sandwich cross section, and when you have the tubes in here, as you can see here, the heat which is being transferred by the tubes to the concrete, they remain in the lower part, and that is exactly what we need to put them to the surface. It is not the point of storage. I will come back to the storage, but it's also the point of comfort. And with this system, we have the comfort. As you can see here, the difference between the cross-section element, this is the red line, and the blue line is the cross-section which is fully like a flat slab. And we start here to bring energy into the room, 12 hours, and then 12 hours we do not put any energy into the cross-section. You can see here we rise up with a very good performance of the system, quite high performance, and the cross-section, the full cross-section, does not bring up these performance as here. But here you see the advantage of the storage, that when we do not heat, here put in additional energy here, we have potential in the cross-section, the full cross-section, and we do not have such high potential in the savings of heat storage with the sandwich cross-section. That is the difference between these two elements. And I just want to show you some pictures how we do that. You can see here the installation of the system. And the point is that we can realize the sandwich cross-section only by prefabricated element. You will not come up with a hollow area like as is shown here with a normal construction on site. You just need to have prefabricated elements, as you can see here. Additionally, you can use the area between the two slabs for all the insulation of the building. And I just want to mention the difference between the point that we bring the energy by the ceiling and to bring the energy by the floor. You can see here clearly the area here, the ceiling area is completely free, and you can bring in the energy into the room by this huge area. And compared when you look here, when you bring in the energy by the floor heating or floor cooling, it is not possible in all the area because you have different elements being placed in the room, and they do not prevent the energy just coming into the room. I think that is the one big advantage. The other advantage is that you use here radiation, and here you have convection. And in this case, you heat up the elements in the room, and in this area, you heat up only the air in the room. And I think that is very essential when you look at these tap system, what we're looking at. As I mentioned, the cross-section can only be done with the prefabrication, and you can see here that we put the tubes exactly very precisely into the slab system, into the lower part, as you can see here, or in another area here. They are very precisely placed, the tubes, as you can see here, that you can do that exactly in the fabrication plant. You bring them to the construction site, and as I mentioned, this is a huge area, about 20 square meter, which is free to bring the energy into the room. And then additionally, you have to connect all these elements, as you can see here. These are the elements in the lower part of the shell, and you have to connect them all together, and that is what we're doing here. And this is also done by our company. We finish all these things all together. As you can see here again, and we put them to a distributor, as you can see here. So the whole system runs when we finish our work, when we finish the structural work, then also the work for the heating and cooling and also for the ventilation, as you can see here, is done. Additionally, we have another slab system, which is completely prefabricated in the plant. As you can see here, it uses also the cross section. It is pre-stressed, therefore it can be very thin, and you put them on the construction site. This is more used for our buildings, not for the office buildings, for the other buildings, houses, these kind of slab system. Then you do not have any additional concrete work on site. I think that is a main advantage. We made a lot of experiments and we did measure all these things, and we have the small office buildings with 4 people working in there, and we could measure all these elements inside. As you can see here, this is a concrete floor, this is a concrete ceiling with a sandwich cross-section. We have a large area where we have the window, sun and heating comes in and cool comes in as well. And we measured all these things, and you can see here clearly, this is the temperature of the room. We bring in energy in here, and then the temperature in the concrete element, it rises up about 6 Kelvin, and the surface of the concrete is going like this, but the room temperature does not change so much in this way. And you see that is one big advantage. Here again, you see the temperature curve of the room. This is the temperature curve of the surface of the concrete ceiling. And we made some interesting measurements. You can see here, if we put in within 8 hours, we put in energy, we raise up the temperature, and we measured the energy going in the concrete and measured the energy going out of the concrete. We put in 100% during this time, and only 25% of this energy is being released immediately into the room, while the other 60% is being stored in the slab, and it can be used during the next 16 hours, as you can see here, to heat the room as it should be done as normal. And after this time, after the 16 hours, we reach the temperature again, what we had in before. This idea or this procedure can be used for an interval, bringing the energy into the room. As you can see here, clearly, we have the idea that that we have heating, and then we have no heating, and you can clearly see the temperature of the room doesn't change so much, as you can see here, but the temperature of the concrete, they change in a certain way. And here you see the temperature, outside temperature, and we can exactly keep the temperature of the room by this interval. And that is very essential for heat pump working, because then you can use the heat pump, for example, when the power is cheap, or when you have the power, and then you can trust on the storage of the energy. Here again, you see we bring in the heat, no heat, we bring in the heat. That is by the transfer of the heating, and the heating going into the room is this line. It is more or less constant, but the interval bringing energy to the system can be in a certain interval. Here again, you see a slide, what we checked again for several days. We put in the heat in here. You see the temperature, the transfer of the energy to the room rises up. You see here the watt per square meter. It rises up, and then we dropped it, and then it falls down, and you see here again the temperature of the ceiling, the temperature of the room, and then we stopped it for 7 days, and during these 7 days we lost about 2 to 3 degrees of the temperature in the room, even though we have outside temperature which is about 0 degree. And the interesting thing is that we have, for example, here, we have sun going through the window, and then the temperature rises in the room according to the solar application of the window. But here you can see clearly by the line here, this one, that the energy is being collected by the system, by the ceiling, and then later it is giving back to the room. This is the self-regulation of the ceiling, and you can clearly see it. And we also tested the concrete wall inside. This is the heat transfer of the concrete wall, and the concrete wall as well takes the energy and put it back to the room when the temperature change. I think that is one of the big advantage of the concrete element, that it also works in a way by no special regulation. So the idea is.
Sorry, sorry, Mr. Friedrich, for interrupting. We're just a little bit running out of time.
I finished now. Huh?
Perfect, perfect.
Okay.
Thank you.
So you can see this later. The idea of us, this is my last slide, is I was talking on the distributing energy by the ceiling, and we are working with additional concepts, taking the energy outside from the surrounding, collect energy, and we store the energy, for example, in the foundation slab. And this is my last slide. Thank you very much, and you can connect me and talk with me. Thank you.
Thank you very much for these insights. I know it's always so much more interesting detail than there is time. Many thanks for summarizing. The next topic will be about refurbished buildings, refurbishing buildings, maybe better this way. Thomas Ramschak, it's your stage. Feel free to share your screen.
So thank you very much. Can you see my screen?
Yes.
Okay. Yeah, thank you very much for the kind introduction. I'm really happy to have the opportunity here today to present our approach together with the other experts and to share experience on how existing building masses can be thermally activated and used as energy storage. I just short briefly about myself. So I come from or have a research background and spent 12 years at INTEC as researcher, where I worked on the development of an energy active facade system, and with Tower 3000, we are now bringing these research results, especially the SEPA energy facade, into real application and into the renovation market. And this is where I would like to start the interface a little bit between energy flexibility and renovation. And in the actual environment, we already have significant growth of renewables, which means more volatility. And the volatility is here to stay. And from our perspective, new business models have to be developed out of this volatility. And in particular, business models related to energy flexibility. So basically, I would say a new revenue hub of opportunity for prosumers or aggregators managing prosumers' portfolios. And in this axis, we see the buildings and its inherent energy flexibility are in particular are key. So we see that the buildings undergo a transition to net zero emissions, where energy efficiency and also the electrification, these are the main drivers. And this transition relies on already available technology, so including improved envelopes, including material efficient building design, and some sector coupling technologies, which are able to transform, I would say, in an easy way, new buildings to resilient energy flexible systems. But it's not that the same case for existing buildings. So an upgrade is often only possible under very difficult conditions. But we also have to tackle this part of our building stock because we know, yes, 90% of the building stock will still be standing also in 2050. So we have to at least double renovation rate and also have to go for deep energy efficient renovation. And what we are doing at Tower 3000 is working on energy active facade as a renovation concept to, on the one hand, save time in the renovation process, to lower the disturbance for the users, to increase the user acceptance, and tackling also the lack of the workforce and reduce life cycle costs. And we see the modularity, the prefabrication, and industrialization of the building envelope kits. These are, from our perspective, the key strategies. But we go a step further and integrate also an active layer into the facade, so to basically heat and cool the building from the outside. So we renovate in one step the hull of the building, and in the same step the energy distribution and heat emission system, and bring it to new building standard. And by doing so, it's possible, but in our case also necessary, to activate the total amount of the building mass of the existing outside walls and use it as active energy storage. And this approach allows us to transform also the existing building into, I would say, an active player in the overall, you can say, energy flexibility game. Before I go a little bit deeper into the technology itself, I would like to give a bit of insights into the market potential for Austria. We know that the buildings from 1945 to the 1980s, they have the greatest energy reduction potential, especially where the buildings have undergone little or no thermal energy renovation measures in the past, meaning these buildings have a heating requirement which is more than 100 kilowatt hours up to 180, 200 kilowatt hours per square meter a year. And these buildings have to be also tackled. And this is a massive challenge. So we have a backlog of more than 1 million residential units in multifamily houses, which have to be renovated in the next years. And to more or less reduce their energy demands, achieve our overall climate goals, and also avoid stranded assets. Here is a picture of our system components. It's general like a wall heating system, which allows us in a very efficient way to heat the building from the outside. So of course we have our core elements. We have the TCP energy distributor. It's heat conducting plate, but with a special shape, which on the one hand distributes the energy from the pipes to the existing wall. But on the other hand, the specific shape enables, and this is very important for us, a very fast assembly of the construction on the construction site, because we all know the labor costs. These are the driving costs, and we have not enough blue workers, so efficiency is the key. It's a water-based system, so of course we can heat the building, but we can also cool it from the outside, and cooling is becoming also increasingly important. So this summer, the media everywhere reported how temperatures, especially in urban buildings, raised far above comfort levels, which could also bring risk for heat vulnerable persons, older persons. But we also hear it from the housing association that cooling is becoming much higher priority. So from an energetic perspective, we have typically in the summer the nice weather, we have a lot of renewables in the grid, and also the highest cooling demand. So basically a perfect match, I would say. But the key advantage of our technology is this minimal invasive approach. So we upgrade the building envelope and the entire heat distribution and heat emission system and bring it to new building standard and everything from the outside. So this means the residents can stay during the whole renovation process in their homes as no work or little work inside the apartments is required. And in realized projects and those under planning, our system function as the sole heating solution and typically fully meets the required heat demand. So the existing radiators can be removed. The outdated pipes, which are also often at the end of the life, can be easily disconnected. In the design phase, so we conduct high resolution heat flux analysis for the existing walls, providing us precise data for the system design. But in general, the poorer the walls, the more efficient our system transfer heat through the walls. It's basically just physics. And we have a project with a wide range of different wall constructions. So we had really bare concrete walls with high thermal conductivity in the industry. But in residential buildings, we often have buildings from the 60s to the 80s. We have a multi-layer construction with 2 or 3 centimeters of Heraclit inside and outside and concrete in between. Or we have bricks, which have U value for the total wall, which is about 8.9 to 1.3 watt per square meter in Kelvin. And this graph shows the specific heat which can be transferred through the different walls with different temperatures or at different temperatures levels for cold climate conditions. But in operation, of course, we reduce the temperature level with a heating curve depending on the ambient temperature and the heating loads. A key benefit of our system is, of course, the energy flexibility. So it is, of course, as the other system, also a slow reacting system, as energy is released into the interior with a time delay. But this inertia also becomes an advantage when you want to operate your system at specific time. For example, when you have, or when the electricity prices are low, you have renewables local, or you are part of a energy community. But also on a larger scale, this energy flexibility can also help to reduce peak loads, for example, in district heating systems. And during my time at AE INTEC, I also co-authored a scientific paper with colleagues where we assessed the flexibility potential and the related cost savings for these energetic facades when they participating in flexibility markets with fluctuating electricity prices. But for time reasons, I cannot go into too much details here, but you're welcome to look up for further insights. Instead, I would like to go further into real scale implementations. So you can see here our first project, multi-family house, a South Australian settlement where our SEPA technology was installed in a conventional way, meaning that our heat conduction plates was mounted on the wall in the first step. Then the pipes were integrated, followed by the application of the thermal insulation and then the facade cladding. What you can also see here in this picture here at the left, we have different heating circuits. So each room and each apartment has its own and can be measured independently. So, which is also relevant for individual billing of the heat for each apartment. And on the other hand, each room can also be controlled individually. And this is also for us a kind of flexibility which allows for flexible use of the space with individual adjustable set temperatures. So you can have, of course, 22 degrees in the living room, but also 80 degrees, for example, in the sleeping room. And we used this project also to talk with the residents to get feedback, especially related to comfort, and the personal feedback was very, very positive. If you want, we have also a short video of the whole construction on our YouTube channel, where you can also see how this system is installed. The second project is a project for the industry, where it was crucial that the production could continue throughout the entire renovation process. And from an energetic point of view, the company makes use of excess heat. So that is otherwise no longer usable at its temperature level. So the energy is used, the excess energy is used for heating the building in the winter, primarily in the supply-driven manner. And in the summer, they have a ground water well for free cooling the facility. So they also cool it in the summer. Here you can see also on the facade, PV is installed, but this is not only used for this building, it's used for the whole production site. Here we are involved in the largest Austrian research project dealing with zero renovation. It's the Renvelope project, which is also led by INTEC. And in this project, 2 buildings will be renovated this year with prefabricated facade elements, where our SEPA system is integrated in these prefabricated facade elements. So we developed specific components which allows that our system can also adjust to uneven surfaces to have a good thermal contact between the heat distributor and the walls. For example, in this project on the left, this project was built so uneven that we have to compensate more or less 6 centimeters. And since the finished facades have or is supposed to be perfectly straight. And here just a few pictures of a production and assembly process. So where we also learned a lot for further optimization of our components, which are already implemented. And I think just to sum up, so our new technology, I would say, brings speed for high deep energy efficient renovation. It brings also acceptance for the different stakeholders and with a lot of co-benefits, which I have already mentioned. And of course, we can also transform with this concept existing building to be part of an overall energy system. So thank you very much. That's all from my side.
Thank you very much, Thomas, for all these insights. Very interesting new technologies. Learn a lot today. So we can directly move on to Shady Attia. Feel free to share your screen.
Yes, so good morning, everyone. Before starting, I want to recognize these insightful presentations that we had just before me. I appreciate this perspective, and I think we have very good quality content shared already. And I want also to acknowledge my colleagues who dedicated their work and collaboration, because my presentation is reflecting a group work. So I will acknowledge them during my presentation. So let's start today's presentation. I have here another task. I am here looking more to step back and look at Europe's role and the market and policies and how they are allowing for the enabling the technology. I'm trying to explore with you what's the situation so that you can have an idea. And the title of the presentation is Legislation and Regulation as Enabler for Flexible Energy Storage in Buildings. So first of all, to start with is that we know that thermal activation works technically. And the question now is, will Europe's rule market and policies allow to scale it up? So we need to look at that, and we were lucky to have a study. It is not fully representative for all European 27 EU member states, but at least it gives us a snapshot on what's going on. We had a study with interviews and literature review covering Germany, Denmark, Belgium, and Spain. And we were focusing on the EU reforms and the unlocking potential for using building mass flexibility as an important topic. So when we look at the energy and building policy landscape between now until 2050, we can see that there are 4 EU laws that will reshape the landscape in the next 25 years. And one of the most important of them is for sure the EPBD, or the Energy Performance Directive of the European Union, that recognizes smart readiness and flexibility, but each member state must translate it in its own way by 2026. And this is our moment to insert thermal storage indicators in these reforms. Another important 2 regulations that are also forming the landscape, which is the EED, or the Energy Efficiency Directive, and the Renewable Energy Directive 3, which formally define the demand side flexibility, and they are opening for procurement for it. So those are also very important one, and they have their own targets. And the last important regulation is the EMD, or the Electricity Market Design, which looks at the reforms to ensure aggregators that can trade that flexibility. And here we are focusing more on the grid action plans to build up a digital background for the whole EU, and to start to trade using data streams, application programming interfaces, smart meters rolling out on large scale, and look at quarter-hour scheduling possibility. So together, those 4 regulations, they are forming the landscape on the short term till 2030 and on the long term to 2050. And we can see that buildings could become active grid assets if the policy explicitly values their stored heat. So this is important to look at, and I think we need to make more lobbying and efforts in bringing the voice from the science and from the practice to the policy, so that we can make sure that this quality, or this storage capacity and flexibility in the building thermal mass can get more forward. Another important thing is that just last month, the EU moved to the 15-minute day ahead settlement. This is meaning that we have 96 price points, and those points are perfect for preheating and pre-cooling building mass when electricity is the cheapest. And based on those 96 day, let's say, points per day, the pricing, we can combine the smart meter data with the capacity tariffs. Like, for example, in Belgium, we have here the 15-minute peak law, and then the tabs can suddenly have their economical signal kicking in the grid, and we can directly see the economical benefit and the exchange of signal between the building and the grid. So here, flexibility is not anymore theoretical, it's already part of the game, and we have some case studies and buildings that are benefiting from this new reform. We have it seen now from a cost point of view on the billing. It will show up in the next months once we start to compare the 2025-26 with 2023-24. So this is also important to look at. When we look at our analysis that we did in the 4 countries and the different feedback we received from the interviewees, they mainly we focused on 3 aspects: the awareness about the systems and tabs in general, the market readiness, and the optimism overall. And you can see Denmark is ranked one of the highest in this classification, followed by Germany. Also, Belgium is on a high side. Spain maybe less, and Southern Europe also on less in general. And when we ask experts like Bjarne Olesen, they say like people think tabs are slow, but they are stable. Andres Valveda Peña said there is no active barriers, only missing incentives. And an expert like Lieve Helsen says that architects reject what they never tried. So this is the fear of what you don't know. And for sure, you can see also expert like Ting Xue saying that massive storage, not just structure. So the storage here comes as a very important factor and lever that we can work on. Now, moving to the EU-wide barriers and the policy pathways, when we look at what we have so far, we can see that when we analyze and classify the barriers from a regulatory point of view, or the regulatory invisibility, the energy performance certificates and the energy performance of building directive, they ignore this dynamic storage capacity so far. So we need to add a flex KPI in the EPBD, and this could be added to Annex 1. So this is very important as actions to modify and reform policy. Second, market access is until now only under 1 megawatt threshold, which excludes building. So we need to implement aggregators that allows for access of lower capacities. And number three, one of the also recognized problem in the whole construction sector across all Europe is the skill gap. We can see that we have very few trained engineers in model predictive control and in tabs in general. And we're glad we have a presentation today of a very well known and seasoned engineer who's showing how they are doing the sizing and customization and the prefab element design. So here we need to have or tackle the EU Pact for skills. And one of these skills modules has to go for these systems with model predictive control. When it comes to the awareness demonstration, awareness and demonstration, so far we are unable to bring mass data sets for policymakers, so make them seeing it white and black clear that we can have energy flexibility through tabs. And in this sense, label flex ready buildings and the Horizon to EU 26 calls can be part of that as a potential for stimulation. Now, to unlock the flexibility, I summarized our study that we did collectively on 4 points. First of all, we need to have a regulatory recognition to put flexibility KPIs in the EPD. Second, market access is important. We need to have open aggregators to sub 100 kilowatt assets. Third, skills need to be trained, architects, facility managers, engineers in predictive control in general. And fourth, demonstration projects need to play larger ampleur or larger impact and magnification. Maybe we need to have a data base for these projects to show, okay, different climates, different clients, different users, and what are the benefits, and show this flexibility readiness of the buildings, make it more visible as they fund also PV roofs. So like we have the PV, we can say also tabs are part of the equation and part of the game. Now, before closing my talk, I want to make sure that in any case, thermal storage will be the hidden engine of carbon neutrality. And I hope that this message gets clearer and clearer, and it will get clearer in the next years. Without storage, we cannot balance what we have from renewables with the demand we have in the building sector. So storage will be key, whether it's on the building level or it's on the district level or even on cities level or national level. So it's very important to look at that. And in this sense, by 2030, tabs and other thermal storage system can provide more than 10 gigawatt flexibility potential in Europe, which is equivalent to 15% of the building sector load. This is very important to look at. Also, by 2050, climate neutral Europe will be fully electric. And this fully electric Europe will be heating dominated with intermittent renewable energy systems, which means that buildings must serve as flexibility sponges. So this is also a key message. And this means that we will have risk If we only focus on timber and lightweight construction, we will reduce the thermal mass and we will have issues in the balancing. I'm not saying here we shouldn't build in timber or in bio-based materials. On the opposite, we will have a surge of these technologies because we want to have a low carbon impact. But in the same time, we need to couple the timber and lightweight construction with thermal mass to make sure that we can control the building and stabilize comfort and exchange with the grid and achieve this flexibility. So here we need to have a strategy and we need to have hybrid cores for our buildings, PCM ceilings or concrete modules or structural storage, you name it. There is a series of technologies. One of them, tabs, is definitely one of the most low-hanging fruits, in my opinion, when it comes to the strategies of structural storage. Some closing words before we open up our discussion. When we look at the aligning technology and the market policy on the long term, we have already proven our case that empirically, through our task 43, we can show that tabs can shift 4 to 6 kilowatt hour per square meter a day with a very minimal comfort deviation, less than 0.5 degree Kelvin. So this means that they're operating very well, and with predictive model control, they can be very performing. When it comes to the grid and system potential across the EU, activating thermal mass in tertiary or office and similar building, and also in the residential building, could supply up to 10 to 12 gigawatt of short-term flexibility. This is equivalent to a large pumped hydro plant fleet, but also the good advantage that this will be decentralized. And this is very good because when it's decentralized, we can stabilize our grids on the district level, which is very much wanted. And from the market point of view, the new 15-minute day ahead market and the aggregator access under the electricity market design reform can create a real economical signal for demand side flexibility. And then we can see a building without tabs compared to a building with tabs can have a very high or a significant advantage. When we look at regulatory inertia, because those are all kinds of layers of inertia like lasagna building up, they will maybe show up by 2035, end of 2030. Current EPBD or Energy Performance Directive and Energy Performance Certification methodologies, they still remain lagging behind, quasi-static, excluding dynamic storage behavior, and there is no regulatory or financial credit given in the thermal mass flexibility. It's recommended that this becomes more an aggressive reform to level it up to the expectation of the market. But anyway, as long as the market will create a demand, I think this lack or this delay in the regulation will be catched up. But for sure, because we are 27 EU member states, every country will have leaders and then we have people laggers until we have a balance. And finally, we will need to have a strategical policy path so that we can incorporate thermal storage indicator in the EPBD and in the smart readiness indicator set, and lower the aggregator threshold to less than 100 kilowatt and launch an EU programs for flex ready buildings and promote them and see them also, like I said earlier, like PVs or like a battery in an electric car. They have an equivalent quality to bring in order to assure the flexibility of the grid. Well, this is the end of my presentation, and I thank you for your attention, and I'm looking forward that we open up the discussion and move on with our session.
Thank you very much, Shady. I think it's very nice. A lot of input, shortly summarized. I think there's a lot of work going into to have it this much summarized. I appreciate the phrase "flexibility sponge." To be honest, I will use it from now on, I guess. Okay, thank you to all the speakers. I think you can see that there's a lot of work going into all these results, and there's a lot of hand-on and really already solutions in the market. Yes, so the questions are open. So if anyone here is having one question, you can raise a digital hand. It's one of the signs you can see on the bottom here. If you cannot find it, just speak up. I guess we can manage. Or if you want to write into the chat, this is fine as well. I just have to read the questions to be it on the recording. So anyone have any questions? Okay, maybe Oh yeah, we have a clapping. Thank you, John. I guess it's for all the speakers. Do you have a question, or is it a yes? Please go ahead.
Yes, I could come up with the first question to Walter Becke. We have shown us the typical flow temperatures, the median flow temperatures for heating and cooling. And the heating was 30 degrees at the ceiling, 27 at the floor, and 50 degrees for the wall. And this was quite high. And the reason was that you supply all this heating load through the wall. And now my question is, if we apply the SEPA system we have seen just as a base load and maybe deliver a peak load inside the building, then the question is, can we come down, can we lower these flow temperatures also for the walls?
I think this is actually a question for me and Thomas. So
Yes.
I give you my perspective first. So this refurbishment of existing walls is possible, but it highly depends on what walls you meet. So if you have a wall that has good heating conduction, then it works pretty good and you can lower the temperatures. But if it's a wall that has, well, lots of air inside or whatever, funny materials, then you have to have higher temperature levels. So I think you have to know very precisely what your existing wall consists of, and then you can design the elements you put on the outside, and also find out what temperature level is needed to get the heat or the cold into the room itself. Of course, you can also add some extra insulation on the outside to make sure the heat goes to the inside and not to the outside. But I think these are the elements you can play with in designing it. So Thomas, now it's your turn to add something.
Yeah, thank you very much also for your answer, Walter. So you have shown one of your projects. What you are looked on directly was this this building with our technology. So it was really on a design that they thought, okay, they really needs 50 degrees. This is also part of a research project, and they did a good measurements. And what I know, they already reduced the flow temperatures much lower. It's not 50, it's around 40 for a very cold climate. So it's really when you're calculating the heating loads, you have to take really everything into account. Typically, the heating load, when you do it like on a basis with for a norm, then you have much higher heating loads that you are really have. So this is what we know. But also when we talk about heating losses, it's physical, given that the heating losses are higher in a system where the rooms are heated from the outside rather than from the inside. But here I would mention 2 points. So on the one hand, we aim in our projects to minimize the transition losses through the outside with very well insulated building envelopes. So the new facades have around 18 centimeters of insulation, where it can achieve a thermal resistance of I think it's about 5.8 something square meter watt per square meter Kelvin per watts, which simultaneously reduces both the heating load, but on the same also the required operation temperature of the wall. And in the design phase, okay, it could be 40. However, we operate the system not it's this temperature the whole year and also not 24 hours a day. And the Südsam project, they did a comparison with a simulation study, a comparison between our system and the system with low temperature radiators, and they looked at the final primary energy demand. And there are research reports on that, and the result was that with our system, the final primary energy demand is approximately 3% higher. So that is very, very low, but also on a very, very low general energy demand. So it's I think it was around 15 kilowatt hours per square meter, 15 kilowatt hours per square meter in the year. And in summary, so while additional heat losses do occur, of course, they remain small, I would say, in very good insulated buildings.
Thank you very much. Yeah. I should have said that all the presentations were very, very good, excellent presentations. Thank you very much for this. And also thank you very much for answering my question.
Welcome.
Okay. Do we, I think we can have maybe one more question, even though it's close to 11. There's someone. Or maybe it's okay if I say, if there are some questions left that people can connect to you directly via email.
Maybe I can ask a second question to you. Can we get these presentations afterwards?
I think I cannot answer. Well, of course, you can get the recordings later on, and about the slides directly. I think we can put it online on the Energy Storage TCP webpage, but only if the speakers agree. I will not say yes or no. They
Yes,
have to.
but I think the speakers are still there and they can say yes or no. But I would be very thankful if we could get the slides
Are
as
you
well.
in the mailing list, John? Because then I will put the link for it in the mailing list, so you know where to find the slides later on.
Okay. Mm-hmm.
I'm not.
I think it's a good idea to put it on the ESTCP, and I think we, the speakers and the subtaskers, we could also disseminate this resource, right? In addition to the YouTube video. It's a good point from John.
Okay. Yes. So if you can just send it to me, and then we put it online on the ESTCP webpage to this one. Yes.
And I have a little request, especially to Thomas Friedrich and also Thomas Ramczak. Your wonderful presentations would be a very good input to the Subtask A report, where we report all these systems. And I would be very thankful if you could make some contributions to my report to this project.
From our case, of course, we can talk afterwards about how we can give inputs to that.
Yes.
John, I know that you are waiting for input from my side.
Yes, yes.
I can send you the presentation, and I also have published now a new publication about this, what I was talking about. I will send you both so we can exchange our ideas how you can implement it in your report.
Well, this would be great. Thank you.
I think in the meantime, there's also a question in the chat, which
Yes.
is much appreciated.
Yes, there was a question from Nigel Gottman about will climate change affect the performance, so as temperatures go up specifically?
I think maybe this is also a question to me. I don't know exactly, but of course, when the outdoor temperatures increase, then you have lower heat loads in the winter, but also at the same time maybe higher cooling loads in the summer. But yeah, the performance will lose less energy during the winter. That's correct. But as I said, we are on a very, very slow level. So it's important to reduce temperatures, but to reduce the heat losses. Yeah, but I think it's more important also to look into the future and into the cooling scenario.
Okay,
I
thank
just
you.
can add something about it. We are talking with clients, and the main concern is the cooling at the days. So the main people, most of the people we are talking with, they tell us heating is not the problem because we have very good isolated buildings, new buildings, but the problem is cooling. And I think that is not so aware at the moment all to the people. And for example, the tap system we're using comes up to a limit, so we cannot bring more energy by this concrete tap system. So we developed a new system which is a kind of booster. Then you can connect it to the concrete slab, and then can get more energy out of the slab on demand. You see, that is, I think, that will be one of the things in the future.
Mm.
Maybe a little remark from my side on this. We expect that our climate will become more extreme in summertime and wintertime. Probably we get colder temperatures in wintertime because we have this Atlantic meridional overturning circulation, which it's getting weaker. And at the same time, the climate can become hotter in summertime. So that means we need more storage capacity. For me, it means we are on the right track.
Yes, I can fully agree. I guess storage is the key for flexibility. Of course, I'm buying this because I'm working on storage as well, but yes, I think I fully, yeah, I guess we're all on the same page. It's just a matter of bringing it to the outside and showing the evidences more and more. So there was before, Christoph, you raised your hand. I'm not sure.
Yeah, I just wanted to underline the aspect of the cooling, and I'm very happy that there were other remarks on this as well, because in Austria we see that the TAPS is gaining traction in the funding tenders because you can heat and cool with just one system.
Yes.
This is maybe one of the obvious but not at first sight aspects that make TAPS more competitive. Mm.
Yes.
When I look at the target range with basically comfort zone of 20 degrees to 24 degrees C, and the model is to get to a steady state throughout the year almost, or at least within the building. But so is there any climate conditions under which it would be too excessive to maintain that sort of target? I mean, is this essentially at the moment the experience is from Austria, which has the temperature range? I wasn't sure from the number of projects how different they were, whether they were very mountainous versus very sort of Vienna based, or I'm just getting a feel for it. This is not critical in any way. It's just trying to feel for it, because you're targeting quite a narrow range in the comfort, whether or not exterior temperatures has an impact. And I fully buy into cooling. In fact, the building envelope needs to be the cooling function in the end, and a weathering.
Yeah, I think maybe to pick that up as the first one, I think to some degree we are maybe less talking about climate zones and outside temperatures, but more talking about building insulation standards. So even in, I would say, moderately cold climates, TAPS systems supplied with lower-ish renewable heat might not be able to cover the heat load of a very poorly insulated building. So this is something that needs to be clear. I have no no known experience to which extremes TAP could go. If you have an insulation standard that you can pick freely, I think, but this is my gut feeling, that it would work well if you have a sufficiently insulated building and also controlled transmission losses. So there I don't really see a limitation. The limitation is more from the insulation that is maybe there in refurbishment, or the insulation that people are willing to pay for in new construction.
Yeah.
But maybe others with more experience in the construction sector want to add to that.
Thank you.
Okay. Anyone of the speakers want to add? Okay. Maybe not, but maybe later. There is still, I think, room for contact later on. Yes, but I also think it's interesting to have a look at different climate zones and different building types and what happens and how it will will work for those. Okay, we have a sign here. Not sure. This is maybe a question. If there's a question, feel free to speak up. Okay.
I have a question.
Yes.
Thank you very much for this great presentation, obviously. And I would like to ask about the cooling part in tabs, or the technology you are presented us today. I would like to ask about the moisture accumulation in cooling. So probably these technologies would work great in dry and cold climates, for good for, I think, Central Europe. But coming to the Mediterranean side, will these applications going to be applied well, or how could possible solutions you have for the moisture accumulation in the ceilings or the walls? Thank you.
Oh, thank you for the question. I think it's very, very, very good. Anyone
Should I
wants to
start?
answer?
I can start with for the walls. So when cooling from the outside is of course essential to ensure that no condensation occurs within the wall. So therefore we recommend operating the system in such a way that the dew point is not undershot. So depending on the climate condition, so the cooling temperature may vary, but in most cases, I would say in Austria, we would limit the temperature to around 18 degree, and recommend then also to use dew point sensors. So this limitation naturally affect also the amount of cooling you can transfer through the walls. The exterior wall cooling system will not be able, I would say, to cool the rooms down to 20 degrees, something like that. However, our goal is to prevent the collapse of the building thermal mass and reduce the indoor temperatures by 2 to 4 Kelvin or something like that. So just to don't get into this temperature range of more than 25, 26, 27 degrees or something like that.
Okay, thank you. Anyone else wants to add something? Yes, please.
Thank you.
Yeah, basically the same applies for the ceilings as well. So you don't go below those 18 degrees centigrade that Thomas mentioned, to make sure there's no rain within the room. So, but I don't have any experience with like going to the south of Europe, how it applies there. So maybe you have to add some ventilation system that does the application. Yeah, I don't know if there's any experience actually with cooling via taps in the south.
Okay. I mean, this is why we connect, to have new research questions, I guess. John, you raised your hand. I guess we
Yes,
can have one.
it's just a remark on the climate. I think we are happy that we live in a climate zone where we have cooling and heating demand, because this asks for seasonal storage. And a seasonal storage can be our ground. The geothermal, shallow thermal, geothermal technology can serve as a seasonal storage. And I think the storage in the building is the natural complement to this. So we have a daily storage, we have a seasonal storage, and the combination of both can help us.
Yes. Thanks, Shady, please.
One little thing, I agree with all what was said before, but to complement what was said, the building must be pressurized positively. And the HVAC system will play a major role in this balance. So there is a lot of examples of tabs in cooling dominated climates. Even in Belgium, we have some types of buildings that are cooling dominated, and we have very high humidity rates. So the pressurizing of the HVAC system and the introduction of dehumidifier in case we have certain thresholds of humidity play a major role. So all what was said is correct, but we should not forget that it's complementary with the presence of a HVAC system that pressurizes the building positively, so that there is also a repulsion of any opportunity that the humidity comes in. And most probably the facade openings will be controlled either mechanically or completely closed, so that there's a full control of the air coming in and getting out.
Okay, thank you. Yes, I mean, I think maybe this will be a challenge in buildings that are refurbished, because they very often do not have a ventilation system yet. But I mean, as I said, this is the new tasks for the future, and the questions that will come up and the solutions that will be found, I guess. Okay, so we are 15 minutes over time.